There are ideas in the universe that intimidate just by being named. Black hole is one of them. Just hearing it is enough for the mind to imagine a dark abyss, a crack in the cosmos capable of devouring stars, planets, even light itself. We grow up with that image, an astronomical monster that swallows everything without distinction, a kind of cosmic vacuum cleaner that silently sweeps through galaxies. But that idea, that almost childish caricature of the black hole, couldn't be further from the truth. The truth is that we misunderstand black holes because we try to explain them using intuitions created for living in a smooth, everyday world where the rules seem simple. But black holes do not live in that world. They are frontiers of spacetime, places where human intuition breaks down, where the laws we think we know stop working as they always have. And while their name suggests emptiness, the truth is that they are the densest, most defined, and perfectly geometric objects that exist. Today, we are going to begin a journey to see them as they truly are, not as monsters, but as mirrors that force us to confront the most uncomfortable fact of all. The universe is not built to be intuitive, and black holes are the most conclusive proof. Imagine for a moment that you are observing a star, not just any star, but a gigantic, massive, brilliant one, thousands of times larger than our sun. For millions of years, it has lived in a perfect balance, ignited by an internal war between the gravity trying to crush it and the nuclear energy trying to expand it. But little by little, its fuel runs out. The balance breaks, and then something occurs so violent that it surpasses everything our mind can grasp. The star collapses in on itself. It doesn't explode outward, or not only outward, it also implodes. It collapses, compresses, shrinks until all its mass is concentrated into a point so small, so incredibly dense, that the very structure of space-time is forced to surrender. And that is how a black hole is born. But here begins the part that we almost always misunderstand. When we think of a black hole, we tend to imagine an absolute void, a gap, a dark tunnel. However, a black hole is not a hole in the conventional sense. It is a real object, with mass, with size, with a boundary. That boundary is called the event horizon. It is not a wall or a physical surface. It is a mathematical region of space where light tries to escape and fails. From the outside, the black hole can be enormous or small. It can rotate. It can have a charge. It can deform the space around it as if it were a sphere sunken into a cosmic fabric. But most importantly, it does not absorb everything near it, as the movies suggest. A black hole is not a desperate magnet or a hungry creature. If you replace the sun with a black hole of the same mass, the planets would continue to orbit in almost the same way. It would not swallow us. We would continue to spin peacefully, though without light, of course. Why then do we imagine it as an unstoppable devourer? Because from our human perspective, accustomed to simple forces and solid objects, it is almost impossible to understand that a black hole does not suck. It deforms. It does not pull. It bends the space around it to extremes that no other object can reach. And this distortion is so profound that light, that universal messenger that always finds a way, gets trapped. When light cannot escape, neither can the information trying to tell us what is happening inside. That feeds the mystery, and the mystery feeds the misunderstanding. The reality, however, is more interesting than the fantasy. A black hole is not a pit. It is a region of the universe where time advances in such a distinct, stretched, and tilted way that for a falling object, the future inevitably points inward. No matter how fast it tries to escape, its future always leads it inward, and no one can escape their own future. Perhaps the best way to imagine this is to think of a river flowing toward a waterfall. If you sail downstream, you can row and stay afloat while the current is gentle. But there is a point where the water runs so fast that no vessel, no matter how hard it tries, can swim against the current. From that point onward, you move with the water toward the fall. That point is like the event horizon, and the waterfall would be the singularity, the impossible core of the black hole where our equations fail. It is important to understand this right now. A black hole is not the destruction of spacetime. It is an extreme geometry of spacetime, and that difference is crucial. If you think of a black hole as a monster, you miss the truth. If you think of it as a strange object, but one that obeys profound rules we are still trying to decipher, then you begin to see its beauty. But the most surprising part is still to come. The black hole not only challenges our understanding of the cosmos, it forces it to evolve. When an object falls into a black hole, the journey is short for it. But for an external observer, that object appears to stop at the horizon. They never see it fully enter. The light it emits is stretched, cooled, and fades. It is as if the matter is frozen at the edge, slowly diluting into an increasingly weak glow. And that illusion, only an illusion but a powerful one, is a window into the black hole's deepest secret, that space and time do not behave as we believe. That is why black holes are so difficult to understand. Not because they are complicated in their mechanism, but because they demand that we abandon our intuition. They ask us to accept a world where time can be bent, where light can be trapped, where energy and geometry merge into one thing. And by doing so, they reveal something more unsettling. Perhaps reality is not what we think. Black holes are the limit, the outer edge of human knowledge. Everything we thought we knew about matter, energy, time, and space is tested in their vicinity. And everything we don't understand is concentrated within them. This is the starting point of our journey, a journey not toward darkness, but toward clarity. Because to understand a black hole, we must first accept that we have misunderstood it from the beginning, and only then can we begin to discover what they truly are. The first idea we must leave behind, after realizing that a black hole is not a hungry cosmic monster, is the most persistent of all. The idea that a black hole is a hole. The word is deceiving. The mind imagines a tunnel, a void, a crack. But, as Kip Thorne and Brian Greene explain, a black hole is a physical object, an extremely precise region of space-time, defined by mathematical rules so rigid that no other object in the universe is as perfect in its simplicity. What we see from the outside, if we can see it, is not its interior, but its boundary. An imaginary surface, yet real in its consequences, the event horizon. It is a limit, a line that does not mark a change in matter, but a change in destiny. Before the horizon, light can try to escape. After it, there are no possible trajectories that return outward, not because something is pulling them, but because the very fabric of space is so inclined inward that advancing forward in time is equivalent to advancing toward the center of the black hole. Thorne describes it as a surface of no return, a point where the equations make it clear that the future points in a single direction. From afar, a black hole appears motionless, a shadow suspended against a backdrop of stars. But its presence deforms everything around it. Not a violent deformation, as movies often show, but something more subtle, curvature. That word, so calm and undramatic, hides the key to understanding why black holes are something we essentially misinterpret. For Green, it is precisely that apparent smoothness that makes them so difficult to grasp. Because in our daily lives, nothing curves in that way. We have no human experiences that can prepare us for the extreme geometry that a black hole represents. If we could get close enough, without falling in, we would notice that light begins to behave strangely. Rays trying to bypass the black hole bend, spin, and twist around it. There is even a critical distance, mentioned by Thorne, where a light ray could orbit indefinitely, trapped in a perfect circle. We call it the light ring. It is a place where the universe pushes the rules of geometry to the limit. But even there, everything still makes sense to physics. Everything is calculable, predictable, orderly. The problem begins when we try to describe what happens right at the horizon, not because it is mysterious in appearance, but because perspective destroys our intuition. Physics, however, remains firm. Green insists on something surprising. Crossing the event horizon would produce no sensation. There would be no tug, no sudden darkness, no specific instant when we could say, "Now I've entered." From inside, everything seems normal. From outside, it seems you never entered. That is one of the most beautiful paradoxes that black holes give us. Two observers can see two completely distinct realities, and both can be correct. In his books, Thorne explains this phenomenon as an inevitable consequence of how time stretches near the horizon. For someone far away, the light you emit takes increasingly longer to reach them. Your image freezes, reddens, and fades. For you, however, events continue with total normality. This radical difference in the perception of time is a reminder of something many forget. Black holes are not simple physical entities. They are regions where time and space have reorganized their meaning. If we continue to delve into what a black hole is not, we must correct another myth. They are not objects that devour indiscriminately. They are not vacuum cleaners. If we placed a black hole the same size as the Sun at the center of our solar system, the planets would continue their orbits almost exactly as before. We would not fly inward. We would not be absorbed. The only difference would be the absence of light. This assertion, repeated by Green, shatters a cultural image we have held for decades. Black holes do not suck matter. Matter falls only if it gets too close, just as it would fall toward any other massive object. What makes the black hole special is not its ability to attract, but its inability to let things out. That is the essence that is often lost in simplifications. Everything that crosses the horizon is trapped, not because something is pushing it down, but because there is no longer a path within space-time that leads back out. What we understand as leaving ceases to be an option. But even though it cannot escape, what falls in does not disappear in the intuitive sense of the word. Here appears one of the most unsettling ideas arising from the work of Hawking, Thorne, and physicists of recent decades. The information that enters a black hole seems to be lost, but physics states that information cannot be destroyed. This conflict triggers the famous information paradox, a conceptual problem so profound that it has pitted some of the most brilliant physicists of our time against each other. Green explains that the surface of the horizon, even though it looks like an absolute void, contains an enormous amount of entropy, the maximum possible for an object of its size. This means that the horizon can store information, but not like a hard drive or a perfectly organized file. It stores it on its surface, distributed, mixed, and disordered. It is an idea so counterintuitive that it forever changed our understanding of the cosmos. Up to that point, Entropy had been a concept reserved for gases, for heat, for common thermodynamic systems. But black holes revealed that even at the limit of apparent nothingness, there is structure, there is memory, there is history. And that discovery opened a rift in physics that we have not yet been able to close. Black holes force a unification of theories that do not fit together. Relativity, which describes the universe on the large scale, and quantum mechanics, which describes the universe on the small scale, both work perfectly until we take them to the edge of a horizon. There, they begin to contradict each other. And that contradiction is not a mistake. It is a clue. A sign that the black hole is more than an astronomical object. It is a natural experiment that the universe has placed to show us that we still do not understand reality. Thus, in this second part, we move away from the caricature of the black hole as a shadow that devours stars and begin to see it as it truly is. An extreme geometric object, a region where time acquires a new meaning, a surface that stores information, and a stage where our best theories conflict. At the heart of all this, there is a silent lesson. Black holes do not exist to destroy, but to reveal. They reveal the limits of our knowledge, the fractures in our theories, and the illusions of our intuition. And, above all, they reveal that the universe is far stranger and much more fascinating than we ever imagined. Up until now, we have viewed the black hole as a silent region of the cosmos, a place where light stops, where time is tilted, where information seems to be lost. An object so dark, so perfect, that it seemed condemned to keep its secrets forever. But in the 1970s, something unexpected happened. The black hole spoke, not with words, of course, but with a phenomenon so surprising that it forever changed our understanding of the universe. Stephen Hawking discovered that a black hole is not completely black. Far from being an eternal abyss, it is an object that can emit energy, lose mass, and even disappear over time. This idea, Hawking radiation, was born from a conceptual clash. Einstein's general relativity, so stable and geometric, met quantum mechanics, so unpredictable and vibrant. Where the two theories touched, the boundary of the black hole, something new emerged. To understand it, Hawking explored the space around the horizon from the quantum perspective. In that seemingly perfect vacuum, quantum mechanics asserts that empty space is never truly empty. It is full of fluctuations, pairs of particles that appear and disappear, waves of energy that spring up and cancel each other out. Anywhere else in the universe, these oscillations are so fleeting that they go unnoticed. But near a horizon, the story changes. The black hole's boundary is such an extreme place that it separates these particles before they can annihilate each other. One falls in, the other escapes. And to the eyes of a distant observer, that escape looks like a real emission. It looks like light. It looks like heat. It looks like life. But it is not the black hole that produces the radiation. It is the deformed spacetime that allows it. Green describes it as a quantum whisper, born from the very edge of nothingness. This phenomenon has profound consequences. If the black hole radiates, it loses energy. And if it loses energy, it loses mass. And if it loses mass, it shrinks. Very slowly, almost imperceptibly, but it shrinks. Over unimaginable timescales, a black hole could completely evaporate. It could disappear. The idea is so radical that when Hawking presented it, it shook the scientific community. Something that seemed eternal, an object that not even light could leave, turned out not to be. And so, with a simple quantum calculation, a new question was born. What happens to the information that falls into a black hole if the black hole eventually disappears? This question is the core of the famous information paradox. Before Hawking's discovery, black holes were already baffling. But at least it seemed that the falling matter remained somewhere inside. We did not know how or where, but we imagined that the information of what entered continued to exist in some form. However, if a black hole completely evaporates, what remains of that history? Is it erased? Is it diluted? Does it become something unrecognizable? Physics has a fundamental principle. Information is not destroyed. No matter how chaotic a process is, there must always be some way, however hidden, to reconstruct what happened. But Hawking claimed that the radiation escaping the black hole contains no trace of the original information. It is pure thermal randomness, energy without structure, like the steam coming out of a kettle, hot, dynamic, but holding no record of the vessel's shape. If this is true, then the information that fell into a black hole is lost forever. And that is something that quantum mechanics does not allow. This is where the mystery deepens. Thorne and other physicists recognized that the conflict was real. Quantum theory demands that information survive. Hawking's calculation suggests the opposite. Green describes it as a crack in the heart of modern physics, a crack that no existing equation can close on its own. The paradox is not just a technical problem, it is a philosophical one. If information can be destroyed, then our fundamental laws are incomplete. The universe, as we understand it, would cease to be a coherent system. And if information is not destroyed, then the black hole must have a secret way of releasing it, a way we do not yet know. That is where the horizon takes on new meaning. It is no longer just a geometric boundary. It is an archive. A surface where, according to later works inspired by Hawking, Thorne, and Susskind, information could be stored in forms so complex that they can only be understood as something holographic. The black hole reveals nothing outward, but its surface is full of patterns, fluctuations, and microstates, a kind of cosmological code inscribed on the frontier of reality. And yet, although this idea has gained traction, it is still not a final answer. The paradox is still alive, like an open wound, reminding us that modern physics is incomplete, that we need a theory capable of unifying the two great pillars of knowledge, relativity and quantum mechanics. A theory that we do not yet have, although we suspect that black holes may be the key. Think about this. To describe gravity, we use geometry. To describe quantum mechanics, we use probabilities. Both work perfectly, as long as we do not mix them too much. But a black hole is the ultimate mix. It is geometry taken to the limit. It is probability stretched to the breaking point. It is the place where the universe tells us, your models stop here. What lies beyond you do not yet have the language to describe. That is the true power of the black hole, not destroying matter, but destroying certainties. The most surprising thing of all is that this conceptual battle does not occur in computers or on blackboards, but at the very edge of space-time. Every quantum fluctuation near the horizon, every quantum of radiation that escapes, every bit of information that is debated between being lost or surviving, is a reminder that reality is deeper than we can comprehend right now. In this third part, the black hole ceases to be a simple astronomical object and becomes an intellectual protagonist, a scenario where the war between theories is fought, where every discovery opens a new question, where the most fundamental concepts are called into doubt. It is no longer just a symbol of destruction, but a symbol of uncertainty, of the frontier, of possibility. And the most fascinating thing is that, despite all this complexity, it all arises from a thin, almost imperceptible edge where light stops moving outward. A simple horizon, a mathematical line, a frontier that speaks, but only to those who know how to listen. Long before we observed a black hole, long before there were telescopes capable of capturing shadows in distant galaxies, there was a silent moment in history when a single man, with paper, ink, and a mind exhausted by war, predicted something that even Einstein believed was impossible. That prediction, a mathematical solution born in a field hospital, revealed that the universe could contain regions where space and time collapsed in an unimaginable way. The protagonist of this story was Carl Schwarzschild. He was an astronomer and physicist, and just as World War I broke out, he decided to volunteer. He did not need to. He had prestige, reputation, and a secured place in the scientific community. But he went to the front anyway. There, between trenches, explosions, and cold nights, he received a copy of Einstein's paper where the theory of general relativity was first presented. That text, which would change the world, reached Schwarzschild while his own was crumbling around him. Schwarzschild did something extraordinary. With barely weeks since the theory's publication, he solved Einstein's equations for a special case, a perfectly symmetrical, spherical object surrounded by a vacuum. Relativity equations were known for their complexity. No one expected anyone to find a solution so quickly, let alone under the constant noise of combat. But Schwarzschild succeeded, and what he found was so strange that it seemed pulled from a work of fiction. His solution contained a point where the mathematics exploded, a region where density became infinite, where the curvature of spacetime became unlimited. A theoretical abyss, a mathematical boundary that we would later call the event horizon. And at its center, a singularity, a place where geometry ceases to exist as we know it. For Schwarzschild, this result was as surprising as it was for any other scientist. The idea of a singularity seemed illogical, a sign that there was an error in the calculations or perhaps in the theory itself. But the mathematics did not lie. There it was, buried in the equations, the prediction of an object so extreme that it defied any classical interpretation. When Einstein read the solution, he was impressed, but also uneasy. Despite his genius, he rejected the idea that such an object could exist in nature, not because his equations forbade it, quite the opposite, but because his intuition told him that the universe would not allow anything so radical. For Einstein, this type of collapse was a mathematical artifact, not an astrophysical reality, a curiosity, not a warning. For decades, the scientific community shared that same disbelief. Physicists accepted the Schwarzschild solution as a theoretical curiosity, a boundary case that would never occur in the real universe. It was too extreme, too absurd, too perfect. Nature, they thought, was more moderate, but nature is not obligated to be moderate. Over time, observations began to accumulate, tentatively at first, stars that seemed to orbit a void, regions of space where light bent in strange ways, densities that no normal star could sustain. Then, more clearly, compact objects that were neither neutron stars nor pulsars, but something even denser, something that fit, piece by piece, with the Schwarzschild solution. The universe was showing what mathematics had already seen. Meanwhile, physicists began to study more closely what this solution really meant. Green explains that the event horizon is not a physical edge. It is a boundary where geometry changes, a region where all paths to the future lead toward the center. What Schwarzschild had discovered was not a mathematical anomaly, but a real characteristic of spacetime. However, accepting this was only the first step. They still needed to understand why the collapse was inevitable. How could a star, a structure stable for millions of years, compress to a point of infinite density? The answer came decades later. with studies by Oppenheimer and Snyder, who showed that under certain conditions, gravity has no brakes. There is no internal pressure, no nuclear force, no quantum phenomenon capable of stopping the collapse. If a star is massive enough, collapse is its destiny. Nothing can prevent it. And so an important lesson emerged. The black hole is not a strange object that the universe occasionally produces. It is the natural conclusion of gravity when it acts unopposed. It is as inevitable as the aging of a star or the cooling of the cosmos. But the most fascinating thing about the Schwarzschild solution is not just that it predicted the existence of black holes. It is that it did so with astonishing mathematical beauty. The way the metric changes as one approaches the horizon, the way time is distorted, the way light curves. It is all contained in a single, simple equation. Green says that these solutions have a crystalline elegance, as if the universe were revealing that, even at its extremes, it follows understandable and ordered patterns. The extraordinary thing is that Schwarzschild never knew what he had discovered. He died a few months after sending his solution to Einstein, without imagining that he had opened a door to one of the most revolutionary ideas of the 20th century. He did not see the debates, nor the controversies, nor the observations that would decades later confirm his vision. He did not see how his solution would become the cornerstone of modern astrophysics. And yet, there it is. A black hole was born first in the human mind before we could see it in the sky. Black holes were not discovered in telescopes. They were discovered in equations. They are children of mathematics rather than observation, and that makes them even more mysterious. Because if a handful of symbols written on a battlefield was capable of revealing that the universe contains regions where time stops, what other hidden truths await in equations yet to be solved? In this part of the journey, we went back to the conceptual origin of the black hole, to that silent moment where reality was first seen through the most precise language we possess, mathematics. And in doing so, we discovered another way in which black holes force us to rethink our ideas. They not only challenge our intuition, but they challenge our sense of the possible. A black hole was born on paper, and the universe, in the end, confirmed it. Now we must return to the physical world. We must observe how, in reality, a black hole is born from a cosmic act as violent as it is inevitable, the death of a massive star. Because although mathematics predicted their existence, it was the stars that brought them to life. There is something profoundly human in looking up at the night sky and thinking that the stars are eternal. Their light is so constant that time seems not to affect them. But that permanence is illusory. Every star we see, giant, small, or medium, lives a story with a beginning and an end. And for some, the end is so extreme that space-time ceases to be a stage and becomes the main character. To understand how a black hole is born, we must first understand what keeps a star alive. Inside, gravity relentlessly tries to crush it inward. Every atom wants to fall toward the center, as if the core were an infinite pit. If the star only had gravity, it would collapse in seconds. But a star possesses another mechanism, nuclear fusion. In the depths of the core, light atoms combine to form heavier ones, releasing an enormous amount of energy. That energy pushes outward, counteracting gravity. The result is a delicate equilibrium, a perfect dance between two forces that compete but never yield. For millions of years, the star lives thanks to that balance. Gravity holds it together. Fusion keeps it open. But this balance is temporary. Nothing in the universe lasts forever. A moment comes when the fuel runs out. It all begins with the death of hydrogen. The star, hungry for energy, tries to consume other elements. It fuses helium, then carbon, then oxygen, in a sequence of increasingly costly reactions. Each stage demands more energy to sustain its structure. And although some stars manage to hold on for a while, fusion eventually reaches an insurmountable limit. Iron. Iron is an energetic dead end. Fusing it no longer releases energy. It absorbs it. And when a massive star accumulates too much iron in its core, that core becomes a parasite. It no longer supports the star, but instead destroys it from within. In an instant, the equilibrium of millions of years is broken. Gravity wins. The star's core collapses in on itself at unimaginable speeds. In less than a second, matter is compressed to densities that defy any human analogy. Electrons are forced to merge with protons, creating neutrons in a brutal process. The entire star crashes into itself in an act of monumental implosion. What follows is an explosion whose magnitude surpasses any everyday concept, a supernova. For a few seconds, the dying star shines brighter than an entire galaxy. Its light expands throughout the universe. Its shockwave expels entire layers of matter, seeding the cosmos with the elements that will later form planets, minerals, oceans, and human bodies. And in the heart of that explosion, destiny bifurcates. If the star was not massive enough, the collapse stops. The neutrons form a structure so rigid that even gravity must obey. A neutron star is then born, an object denser than anything outside a black hole, but still capable of holding itself up. But if the star was larger, if it exceeded a certain mass threshold, known as the Tolman-Oppenheimer-Volkoff limit, then not even neutron degeneracy pressure can withstand the weight of the chaos. Gravity finds no opposition. There is no known physical force capable of stopping the collapse. And the collapse continues. It continues until space curves so much that no trajectory can return. It continues until light is trapped. It continues until time itself is inclined toward a single central destiny. It continues until the universe creates an object so perfect in its simplicity that it has no surface, no texture, and no visible internal structure. Only mass, charge, and rotation. Thus, a stellar black hole is born. And yet, this is only one of the possible paths to their formation. The mystery of supermassive black holes. In the universe, there are not only black holes born from stars. There are also colossi with masses equivalent to millions or billions of suns. They reside at the center of almost every galaxy, including our own. They are the dark hearts of immense structures, gravitational engines that organize the movement of stars, gas, and dust on unimaginable scales. The curious thing is that we do not know exactly how they are born. Theories are many, but none is fully confirmed. Green explains that one possibility is that they started as stellar black holes that, over time, grew as they devoured gas, dust, and other stars. But the early universe was too young to allow them to grow so quickly. Observations show supermassive black holes existing when the cosmos was only a few 100 million years old. How could they have grown so large in so little time? Another theory suggests that large clouds of gas in the early universe could have collapsed directly into giant black holes, bypassing the star stage. These enormous, disorganized clouds failed to fragment to form stars, and instead collapsed suddenly, creating much larger seed black holes from the start. Thorne and other researchers have also explored the possibility that direct collisions between supermassive stars hundreds of times larger than the Sun, formed under extreme conditions in the young universe, could generate enormous black holes in just one stellar generation. Whatever the origin, the truth is that these giants grew with impressive voracity. They absorbed matter from the galactic disk, captured rogue stars, and fed on the gas flowing toward the center. Over time, every galaxy became organized around them, as if the black hole were an invisible master shaping billions of stars. It is a surprising contrast. Supermassive black holes are not born from the destruction of stars, but from a universe so young and dense that it did not even need stars to produce abysses. Primordial black holes, the oldest fossils of time. Among the strangest concepts explored in modern physics are primordial black holes. They are not born from stars. They are not born from gas clouds. They are born from the universe itself in its first moments, when it was so hot, so dense, and so chaotic that quantum fluctuations could concentrate enough energy to create mini-spatial abysses. These black holes, if they exist, would be tiny compared to their stellar or supermassive relatives. Some would have the mass of a mountain compressed into the size of a proton. Others would be even smaller. And some, according to Hawking radiation, would have already disappeared, completely evaporating. Thorne points out that the existence of primordial black holes would explain several cosmological phenomena, including the mysterious dark matter. But so far, there is no direct evidence. They are a theoretical possibility, a potential imprint of the physics of the early universe, a reminder that the cosmos may have produced black holes even before it produced light. The birth of a horizon. In all these cases, stellar collapse, direct gas collapse, primordial fluctuations, there is a crucial moment, the instant the event horizon is formed. It is the point where the escape velocity reaches the exact value of the speed of light. Nothing special happens physically in that place. There are no sparks, no flame, no explosion. But something conceptual happens. The universe draws a boundary that did not exist a second earlier. It is a silent birth, a geometric metabolism, not chemical or nuclear. It is not an object that emerges, but a region of spacetime that redefines itself. And that redefinition marks the beginning of a peculiar story. The black hole begins to exist, but not as matter, but as geometry. It is one of the few objects in the universe whose identity depends more on space-time than on the matter that composes it. The black hole is not the material that fell inside. It is the space-time curved by that material. What fell was a star, but what was born is something completely different. The imprint of birth, gravitational waves. For decades, black holes were only theories. No one had seen one directly, and although stars orbiting nothing suggested their presence, something more solid was missing. That something arrived when we first detected gravitational waves. Thorne, who participated directly in the LIGO project, describes how these waves are not light nor sound, but vibrations of space-time itself. They are produced when two black holes collide and merge. The energy released in that collision is so extreme that it makes the entire universe tremble, sending a signal that can travel for billions of years until it reaches Earth. These gravitational waves not only confirmed the existence of black holes, they also confirmed that they are born, grow, meet, and merge into even larger objects. Each merger creates a black hole with a wider horizon, a deeper geometry, a longer history. The universe, in its silent language, was saying, yes, black holes exist, and they not only exist, they dance. The black hole as a natural destiny. In this part of the journey, we discovered that a black hole is not an accident. It is not something exotic that happens only under improbable conditions. It is a natural culmination, a physical outcome, an inevitable consequence of how gravity works when matter reaches extreme levels of density. Black holes are born from stars reaching the end of their lives, gas clouds collapsing without fragmenting, fluctuations in the early universe, violent mergers between other black holes. They are the logical result of laws we know well, strictly determined by general relativity. And yet, each birth holds a mystery. What happens to the falling information? How does space-time behave near the singularity? How does it all fit with quantum mechanics? The physical birth of a black hole is clear. The conceptual birth, not yet. When we observe the universe from a distance, it seems silent. Galaxies move in a slow ballet. Star clusters patiently rotate. Nebulae expand like eternal clouds. Nothing seems to be in a hurry. But beneath that tranquil appearance, another kind of movement exists, one that does not depend on light or sound, one that unfolds in the very fabric of space. It is a vibrant, intense, and almost musical rhythm that for all of human history was occurring without us being able to perceive it. It is the rhythm of black holes approaching, meeting, and merging in a spectacle that repeats throughout the cosmos since before the Earth existed. To understand how two black holes end up joining, one must first accept that space is not a passive stage. It is not a rigid vacuum where things simply move. Space is flexible, elastic, moldable. When a massive object curves it, that curvature changes the movement of nearby objects, and they in turn modify the curvature of space. The entire universe is an act of constant feedback. In the case of black holes, this interaction becomes extreme. They are so heavy, so compact, and so radical in their geometry that they affect space over incredible distances. When two of them exist in the same region, each one tries to shape the space in its own way, and the result is an impulse that slowly draws them closer, as if both were trapped in an eternal dance that cannot end otherwise. Imagine two dips in a stretched membrane. If you place them separately, the membrane sinks in two distinct places. But if you gently push them toward the center, you will see that both dips begin to attract their own deformation, drawing closer, inclining, and deforming the surface between them. Something similar happens with two black holes. They do not attract each other because there is a mysterious force between them. They approach because they are carving a space-time that already contains the route to that encounter. It is not a chase. It is a progressive slide toward a future union written in the geometry. The fascinating thing is that this process is not silent. From the human perspective, it does not emit light or heat, but it does emit something that for millions of years was completely invisible to us: gravitational waves. These waves do not travel through space like light. They are ripples of space itself. They are similar to the marks left by a stone dropping into a lake, except that here there is no water and no surface. What vibrates is the structure of the cosmos. Thorne describes these waves as a kind of echo, a testimony to the changes occurring in very distant regions of the universe. They are delicate, subtle, almost imperceptible. However, they contain precise information about the mass, speed, and rhythm of the black holes that generated them. For decades, these waves were a theoretical prediction. We knew they must exist, but no one had managed to detect them. Not because they were not there, but because they were too small for us to feel them. When a gravitational wave passes through Earth, it stretches and compresses the entire planet, but it does so by absurdly minute proportions, much smaller than the diameter of a proton. It is like trying to detect the movement of a mountain caused by the flutter of a mosquito on the other side of the world. And yet, we succeeded. Before getting to that story, let's return to the black holes. As they orbit one another, each turn brings them closer. Each turn sheds a bit of energy, because the gravitational waves carry part of that energy away with them. It is a slow process at first, almost imperceptible. For millions of years, black holes can orbit each other at large distances without an appreciable change in their trajectory. But as the dance intensifies, the rhythm changes. They begin to spin faster. The space around them stretches, twists, and ripples. The event horizon of each one begins to slightly deform, like droplets that elongate when they are about to merge. When the distance between them is small, the orbital velocity skyrockets. In the final seconds before the merger, two black holes can orbit each other hundreds of times per second. It is difficult to imagine from our temporal scale, but in that instant, the universe is witnessing one of the most energetic events it can produce. A collapse of space-time accelerated to indescribable levels. For light, what happens is strange. Space curves so much that the photons attempting to escape are turned back, trapped, and distorted. For matter, there is no hope. For time, there is no fixed rule. But for space, this encounter is a revolution, a transition from two separate geometries to a single, deeper geometry. When the final contact occurs, the horizons merge into a single, larger horizon. It is not a collision like that of two solid objects. There is no crash, no fragments, and no explosion in the classical sense. What happens is a smooth transition in geometric terms, although violent in energetic terms. The union of the two horizons releases an absurd amount of energy in the form of gravitational waves, waves that travel through the cosmos at the speed of light, expanding like a message announcing, two black holes have become one. These waves contain precise information about the final mass, the resulting rotation, and the energy lost during the merger. They are like the acoustic signature of an event we can never see with our eyes, but which we can hear through special instruments. And this is where the human story enters. For decades, physicists like Kip Thorne, Rainer Weiss, and Barry Barish dedicated their lives to building an instrument capable of listening to those cosmic vibrations. A device so sensitive that it could detect a change in the distance between two mirrors, equivalent to 1,000th of the size of a proton. No previous experiment had required such surreal precision. To achieve this feat, it was necessary to build tunnels several kilometers long, use extremely stable lasers, and isolate the system from seismic noise, thermal noise, quantum noise, and the noise of the vacuum itself. Every step was a struggle against nature. That device was named LIGO. For many, LIGO was an impossible dream, not for lack of theory, but because the required technology seemed too advanced, too demanding, too delicate. But Thorne and his team persisted. Year after year, decade after decade, they adjusted every aspect of the machine, correcting defects, measuring errors, and discarding hypotheses. The work was slow, frustrating, and meticulous, but it was also full of hope. They knew that if they managed to hear those waves, they would be opening a new form of cosmic perception, a completely different window from traditional astronomy. And one day, it happened. In September of the year that LIGO finally reached its full sensitivity, a signal arrived from the cosmos. Two black holes, located more than 1 billion light-years away, had merged. The gravitational wave produced by that union traveled all that time through the universe, crossing galaxies, clusters, and cosmic voids until it reached Earth. When it passed, it stretched and compressed the instrument by a measure so small that no one would have imagined it could be detected. But LIGO detected it, and in that instant, humanity heard the sound of space for the first time. The signal recording was not like a light wave or a burst. It was a rising chirp, a note that increased in frequency until it abruptly cut off. That sound represented the exact moment the black holes united. For many scientists, it was a moment as symbolic as seeing the sky for the first time with a telescope or identifying the first galaxies. It was confirmation that our understanding of relativity was not only correct, it was also incomplete, and this new method would allow us to discover its limits. The most impressive thing about these gravitational waves is that they do not rely on light. Light can be absorbed, deflected, and blocked. Dense regions of gas, light simply cannot escape. But gravitational waves traverse the universe without stopping. No matter how many galaxies they pass, nor how much matter is in their way, they advance without losing information. This means we can study events that we had never been able to observe before, events that were literally hidden behind a cosmic curtain. Once the first waves were detected, others began to arrive. Mergers of black holes of different sizes, collisions between neutron stars, and collapsing binary systems. Each signal was a different story, a new sentence in a language we were just beginning to decipher. Astronomy became more than seeing, it became listening. Let's return to black holes. Once they merge, the resulting black hole is more stable, larger, and more rotational. Rotation is important because it influences everything that happens around it. A rotating black hole drags the space around it, creating an effect called frame dragging or the lens thirring effect. It is as if space were a thick soup and the black hole were spinning within it, dragging the fluid along. This means that any object that approaches, a star, a gas, a cloud, will be forced to spin in the direction of the black hole. It has no choice. Geometry dictates the motion. Over time, this black hole can continue to grow. It can absorb gas from its surroundings, swallow stars launched by chance, and merge with other black holes it encounters throughout its history. There are supermassive black holes that have experienced hundreds or thousands of mergers. Each one leaves an imprint on their rotation, their mass, and the way the horizon stretches or flattens. When we observe a black hole at the center of a galaxy, what we see, or rather, what we infer, is the result of a lifetime of mergers, collapses, and violent encounters. Green explains that, in a sense, a black hole is an archive of the universe. Not because it preserves information in an accessible way, we know this is debated due to the information problem, but because its mass and rotation tell a story. It doesn't tell us what fell in, but it tells us how much fell in and how it fell in. It is like finding a crater. You do not see the meteorite, but you know how much it weighed and what direction it came from. The merger of black holes is not a rare event. It is something that happens constantly in the cosmos. Entire galaxies collide with each other on enormous timescales. And when they do, their central black holes end up in a dance that can last millions of years, until it culminates in a final merger. That process is happening right now, this instant, in places in the universe so distant that we may never have visual access to them. But their waves can arrive. Their vibrations can cross the cosmos and reach us when we least expect it. The fascinating thing is that, thanks to these waves, we begin to understand something deeper. The universe is not static. It is not an immobile painting. It is a living fabric in constant tension, in a perpetual state of deformation. Every event, no matter how small, leaves an imprint. A stellar explosion, the orbit of a planet, the gravitational brush between two galaxies. Everything is recorded in space. Everything vibrates. Everything leaves an echo. Black holes are, then, both actors and narrators. Actors, because they shape the cosmos with their extreme gravity. Narrators, because their mergers tell us stories of the past that light cannot transmit. Every gravitational wave is a message sent billions of years ago. And when we receive it, the universe speaks to us in a language that, until recently, was completely unknown. The existence of binary black holes is more common than we imagined. Some stars are born in pairs, and if both are massive, both can explode and leave behind two black holes orbiting each other. These pairs can live together for millions of years, slowly drawing closer. In other cases, the merger occurs as a result of the collision between galaxies. When two galaxies meet, their central black holes begin a dance that can last longer than the life of all humanity. But in the end, the result is always the same: a merger that produces a larger black hole and gravitational waves that expand throughout the universe. This process creates a cycle that repeats indefinitely. Small black holes are born from stars. Some meet and merge, creating medium black holes. These, in turn, can meet others and generate larger black holes. Over time, many end up in galactic centers, where gravity is most intense and the flow of matter is most abundant. There they grow, feed, and accelerate. And if another galaxy passes too close, the story begins again. The entire universe seems to be built around this cycle of birth, growth, merger, and transformation. Black holes are not exceptions. They are fundamental engines in cosmic evolution. They regulate the flow of matter in galaxies, influence star formation, and shape the behavior of entire clusters. Without them, the universe would be unrecognizable. The understanding of mergers not only tells us about the life of black holes, but also about the deep structure of reality. It reminds us that space is not a container. It is an active medium, a dynamic fabric capable of curving, stretching, and vibrating. Every merger is a demonstration that the universe is more like an organism than a machine. It has rhythm, it has memory, it has resonances that travel long after the event has occurred. And the most surprising thing is that we are only just hearing the first notes of a millennia-old symphony. LIGO was the first instrument. Now others exist, such as Virgo and Kagra, which expand the detection network. In the future, we will have spatial interferometers like LISA, capable of detecting even slower and deeper waves coming from mergers of supermassive black holes. When that happens, we will hear stories that have so far remained hidden: collisions between entire galaxies, processes of enormous growth in the first moments of the cosmos, signals that traveled from eras when the Earth was not even a cloud of dust. Two black holes meeting are a reminder that everything in the universe converges sooner or later. Nothing is completely isolated. Everything is connected by subtle paths, sometimes imperceptible but real. Their mergers reveal that even the most extreme objects follow laws that we can understand, and that these laws are so elegant that they allow the universe to express itself through vibrations in its own fabric. Ultimately, observing or listening to the union of two black holes is listening to the universe telling its story to itself. It is a profound, almost intimate gesture where gravity becomes sound, where geometry becomes a message, and where we, tiny creatures on a lost planet, manage to capture a whisper that traveled billions of years to reach our ears. Sometimes the most dangerous questions do not come from the stars, nor from telescopes, nor from gigantic experiments, but from a deeply human gesture: the need for the universe to make sense. And few things challenge that need as much as what happens when something falls into a black hole. It doesn't matter if it is a star, a spacecraft, an atom, or a simple particle of light. In all cases, the question that has troubled physicists for decades is the same. What remains of that identity when the event horizon envelops it? Where does the information go? That essential imprint that describes what an object is? For classical physics, the simplest answer would be to say that it disappears. That everything that crosses the horizon is definitively isolated. That the black hole merely increases its mass and nothing else matters. But that answer only worked before quantum mechanics made its entrance into this story. Because one of the most sacred rules of quantum physics asserts that information cannot be destroyed. It can be transformed, dispersed, or encoded in almost unrecognizable ways, but never disappear. And here the tension begins. General relativity seems to say one thing, while quantum mechanics says something completely different. For a long time, this contradiction did not bother anyone. Black holes were purely theoretical entities. They existed in equations, but not in telescopes or observatories. It was easy to think that perhaps the conflict would resolve itself, or that some yet unknown aspect of the equations would explain the matter. But when Stephen Hawking introduced a new ingredient into this puzzle, the stillness was completely broken. Hawking discovered that black holes are not completely black. In reality, they emit radiation, an extremely faint glow that arises from quantum effects near the event horizon. It is not light like the sun's, nor like a star's, but a much more subtle phenomenon. It comes from the quantum vacuum, that restless sea where virtual particles appear and disappear in fractions of a second. Normally, these particles exist for so little time that they have no consequences. But at the horizon boundary, the story is different. There, quantum fluctuations can split. One particle falls into the black hole, and the other escapes. That particle that manages to flee is what we call Hawking radiation. Over time, this process causes the black hole to lose mass. Slowly, almost imperceptibly, it evaporates. It can take billions of years, even longer than the current age of the universe, but according to the equations, it eventually disappears completely. And if it disappears, the inevitable question arises: what happened to all the information that fell inside? Hawking concluded that the information is lost forever, that the black hole destroys the identity of what it swallows, that the radiation it emits contains no trace of what fell in. It would be like burning a book until it turns into ashes and smoke, except that in this case, not even the ashes retain anything of the original text. This idea was so radical that it divided the scientific community into two irreconcilable camps. On one side, those who supported Hawking, convinced that general relativity was the final word on these for many. Accepting the loss of information implied accepting that the fundamental laws of the universe could be broken, that there were processes that simply eliminated data without a trace. It was a kind of cosmic violation of the natural order. Green expresses this conflict clearly. If information disappears, the universe ceases to be predictable. It ceases to be a system governed by reversible equations. It becomes a place where some processes simply erase history. Even so, for years, Hawking's view was the dominant one. It seemed impossible to find where or how information could be stored in a structure whose external properties were so simple. A black hole, according to the classic no-hair theorems, only has three characteristics: mass, charge, and rotation. Nothing else. It does not matter if it swallowed a star, a planet, or a cup of coffee. From the outside, it looks exactly the same. So, how could it encode complex information if its very identity is so austere? However, the unease grew. Something did not fit. The universe does not usually violate fundamental principles whimsically. Behind every contradiction, a profound revelation is usually hidden. And so, slowly, a new idea began to emerge. An idea that would completely transform the way we understand space and time. The key came from a very particular boundary, the event horizon. For years, the horizon had been thought of as a kind of physical limit, like a thicknessless membrane that simply separated two regions of the universe. But research began to suggest that perhaps the horizon could store information, not in its interior, but on its surface, as if the information of everything that falls in remained trapped there, encoded in a kind of microscopic pattern that we still do not know how to read. This idea gave rise to a powerful notion that the universe, in a sense, can behave like a hologram. In a hologram, all three-dimensional information is encoded on a two-dimensional surface. And although it sounds strange, calculations began to show that the black hole's horizon has an information capacity proportional to its area, not its volume. It is a deeply counterintuitive revelation, but also extremely elegant. The black hole could be acting as an information container where every bit is distributed over the surface, creating a kind of quantum map impossible to visualize directly. Image illustrating the holographic principle. 3D information encoded on a 2D boundary. Here another idea comes into play, one that took shape thanks to the work of Gerard T. Hooft, Leonard Susskind, and many others. The holographic principle. This principle suggests that all the information contained within a volume can be completely represented on its surface, not as a metaphor, but as a real physical equivalence. It is as if the universe had two different descriptions, one inside and one outside, both valid, both complete. If this is true, then a black hole does not destroy information. It simply rewrites it on its surface in such a complex way that it seems lost. Hawking radiation, instead of being completely random, could be subtly imbued with the patterns of the horizon. The message is not destroyed, it is only degraded to the point of being almost impossible to retrieve. But disappearing is not the same as hiding. However, even with these ideas, one problem remained. General relativity holds that someone falling into a black hole feels nothing special when crossing the horizon. There is no explosion, no shock, no obstacle. The person simply continues to fall until reaching more extreme regions. This concept is called equivalence and is one of the pillars of Einstein's theory. But the holographic principle seemed to suggest something different, that something physical must occur at the boundary to encode the information. How could both visions be compatible? To answer, a surprising image emerged, that of the horizon as a type of surface on fire. From the outside, someone would observe the falling person transform into a distorted image stuck to the horizon, being slowly absorbed by that information layer. From the inside, the person would feel nothing special, continuing their fall undisturbed. Both descriptions would be true, but from different viewpoints. It is like observing a map and a territory at the same time. Neither is false. They simply represent the same thing from incompatible perspectives. This duality, although strange, resolves part of the conflict, but not everything, because the deepest point of all remains, the singularity. That mathematical point where curvature becomes infinite is the place where general relativity ceases to be valid. And if the theory fails there, we cannot trust that its predictions about information loss are correct. Many physicists believe that the final answer will come from a theory of quantum gravity, a theory that combines relativity and quantum mechanics into a single, consistent framework. But we do not have a complete one yet. We have fragments, clues, and approximations. String theory offers one possible answer. Loop quantum gravity offers a different one. Both agree on a crucial point. The singularity should not exist as relativity describes it. There cannot be a point of infinite density. Something else must occur there, something that current theory cannot describe. Some scientists imagine that the falling matter compresses up to a certain point and then rebounds, as if the interior of the black hole were a passage to another region of spacetime. Others suggest that the singularity is replaced by a diffuse quantum structure, a vibrant core where the usual laws of space cease to apply. If this were true, perhaps the information is not destroyed, but is transformed into a pattern that reappears in the black hole's final radiation when it evaporates. The most provocative idea is that, in the final moment of evaporation, the black hole could suddenly release all the information accumulated during its existence. It would be a quantum burst, a last gasp where the universe returns what seemed to have been lost. No one knows how it would happen, or what form that release would take. But the important thing is that the fundamental principle holds. Information is not destroyed. In this scenario, a black hole would cease to be the perfect destroyer and would become an extreme archivist, a quantum processor capable of storing inconceivable amounts of data. Its life would be a kind of cycle: birth, growth, transformation, evaporation, and release. At every stage, information would find a way to survive, even if that way is so complex that we cannot decipher it. Nevertheless, the debate continues. Hawking himself changed his mind in the last years of his life, accepting that information is probably not lost. But the definitive solution still does not exist. We are facing a conceptual wall, a limit where our best theories cease to agree. And yet, this conflict is not a sign of failure. It is a half-open door to a deeper understanding. All important tensions in science have been like this. When electromagnetism and classical mechanics clashed, quantum theory was born. When quantum mechanics and special relativity clashed, modern particle physics was born. And now, when general relativity and quantum mechanics confront each other inside a black hole, we know that the clash is not the end. It is the beginning of something greater. Black holes, with all their darkness, could be illuminating the path toward the next scientific revolution. They not only force us to rethink space and time, but also the nature of reality. They show us that the universe is not a collection of isolated objects, but a quantum fabric where information, energy, and geometry are eternally intertwined. Perhaps one day we will discover that black holes are not cosmic tombs, but frontiers to a deeper structure. Perhaps we will discover that information never truly falls, but is redistributed in ways we do not yet know how to read. Perhaps the event horizon is a screen, a code, a projection of a richer dimension. Be that as it may, the information paradox reminds us of something essential. Every time the universe seems to contradict itself, what is really happening is that it is inviting us to look closer, to see beyond the veil, to understand that its logic is broader than ours. On the surface, the universe seems an ordered place. Stars follow elegant trajectories, planets obey precise orbits, galaxies gather in colossal structures that stretch across the void. It is easy to imagine that space, among all those bodies, is a stable stage, a kind of motionless canvas where matter writes its history. But that stability is only apparent. It is the calm we see when observing an ocean from an airplane. Smooth, uniform, almost solid. The true face of the sea is only revealed when we descend to touch it. And the same thing happens with space. Its true essence does not appear on human scales, nor on stellar scales, nor even on galactic scales. We must descend much further, to a territory that cannot be seen or touched, but which absolutely defines everything that exists. That territory is called quantum foam. Image illustrating the concept of quantum foam. Space-time at Planck's scale, showing chaotic, turbulent fluctuations. It is a gentle name for something that, in reality, defies everything we think we understand about reality. According to Green, if we could reduce space to incredibly small scales, scales so tiny that words cease to be useful, we would discover that space no longer resembles a smooth surface. It would be more like a boiling ocean in a perpetual state of vibration. There are no straight lines, no defined distances, and no time flowing uniformly. Only an intense, chaotic, unpredictable agitation. It is a turbulence that is unlike anything we can experience in our daily lives. A turbulence created not by matter, but by the quantum uncertainty itself. The uncertainty principle, which controls the behavior of everything microscopic, dictates that one cannot simultaneously know the position and energy of a point with absolute precision. This implies that even the vacuum, which we usually imagine as nothingness, is not truly empty. It is full of fluctuations, momentary bursts of energy that appear and disappear so quickly that they barely exist. But even if they are fleeting, their presence affects space itself. On tiny scales, these fluctuations shake the geometry, bending it, twisting it, stretching it. Space ceases to be a smooth fabric and becomes a thick broth where every point pulsates. The most surprising thing is that this behavior does not depend on there being something within space. It is a property of space itself. The universe does not need particles to vibrate. It vibrates due to its own quantum nature. And here, the most disturbing part appears. If the geometry of space changes form on these scales, then the very notion of a point ceases to make sense. There is no exact place where something can be because the place itself is fluctuating. It is like trying to point to an object on a liquid surface at the exact instant the surface is breaking into thousands of droplets. Thorne describes this region as a geometric hell, although not in the human sense of the word. It is a mathematical hell, unpredictable, agitated, without simple rules. There are no smooth curves or continuous trajectories. Everything is discontinuous, disparate, irregular. And the most disconcerting thing is that this region is not hidden in a remote corner of the universe. It is under our feet. It is around you right now. Every cubic centimeter of the space you occupy contains this extreme turbulence, except that it is dampened by millions of higher scales. It is like having a furious storm under a perfect glass. We see the stillness of the glass, but not the chaos that exists underneath. Quantum foam is, in a way, the fundamental language of the universe. Everything that exists, atoms, stars, black holes, emerges from that vibrating structure. But understanding it is extremely difficult, because general relativity and quantum mechanics describe the world in incompatible ways. Relativity assumes that space-time is smooth, continuous, and uniform. Quantum mechanics demands that everything be granular, fluctuating, and uncertain. On large scales, relativity works perfectly. On small scales, quantum mechanics is the absolute law. But right where both theories should unite, at the Planck scale, where the foam is born, there is a conceptual crack that we still do not know how to close. Imagine that the universe is a tapestry. From afar, the fabric looks uniform. But when you look at it with a microscope, you discover the threads, the fibers, the intertwinements. Quantum foam would be that level of extreme detail. We do not see the threads of space because our tools cannot reach that scale, but we know they must be there, and that their structure is much more complex than we imagined. Green explains it as a conceptual frontier, a limit where our usual metaphors no longer serve. There is no before or after in the traditional sense. The fluctuations are so intense that time, as we understand it, loses meaning. It does not flow, it pulsates. And here, something crucial comes into play. Black holes. Contrary to what might seem, black holes not only distort space on gigantic scales, they also reveal what happens on minute scales. In a way, a black hole is a conceptual microscope. It amplifies what is normally hidden. The extreme curvature it produces in its vicinity forces the quantum laws to manifest themselves. In regions near the event horizon, the vacuum fluctuations become more intense, more significant. Hawking radiation is an example of this. It is not a classical phenomenon, but a direct consequence of the quantum foam interacting with curved geometry. It is as if black holes pressure the universe, forcing it to show its seams. Where space curves so much that it seems to give way, the quantum foam becomes more visible, more dominant. Not in the sense that we can see it directly, but in the sense that its effects become impossible to ignore. And here, a profoundly poetic idea arises. Perhaps the reason why black holes are so mysterious is because they touch a level of reality that we still do not understand. They are areas where relativity and quantum mechanics collide with such brutal intensity that no single theory can describe what happens inside. The quantum foam, in its extreme turbulence, could be truly responsible for the properties we attribute to black holes. They are not devouring monsters, but windows to the most fundamental structure of the universe. If we could descend to those scales, we would see how geometry turns into a perpetual whirlwind. We would see lines of space appearing and disappearing, tiny tunnels opening and closing in lapses so brief that they defy any intuition. Green explains that the quantum foam can contain mini black holes, small regions where space momentarily collapses into tiny singularities. They are ephemeral versions of real black holes, continuously appearing and disappearing without us being able to detect them. Their life is so short that they do not even manage to form as defined objects. They are just fleeting patterns in a boiling sea. When we think of a real black hole, we tend to imagine its horizon as a sharp boundary. But if quantum foam defines the structure of space, that boundary might not be as exact as we believe. It could vibrate, oscillate, and ripple with the microscopic agitation. For an external observer, the horizon seems perfect. But on the scales Green describes, it could be as turbulent as the surface of the ocean under an invisible wind. Thorne also points out something essential. The singularity inside the black hole is a classical prediction, but in the quantum foam, that concept simply cannot exist as we imagine it. There cannot be a point of zero volume in a space that is not continuous. The singularity, if it exists, must have a quantum structure, something more complex than an infinitely dense point. It is probably a region where space decomposes into forms that we cannot even describe yet. The quantum foam, then, is not an optional scenario. It is the foundation. It is the deepest level from which all other properties of the universe arise. And yet, we are not used to thinking of it that way. We find it difficult to conceive that the solidity of a mountain or the stability of a star depend on processes so chaotic on such tiny scales. But that is the message Green repeats over and over. What we see as stability is simply the sum of balanced fluctuations. The apparent calm of space is the result of a delicate equilibrium between quantum vibrations that, when averaged out over large scales, cancel each other out. The universe is stable because its fundamental instability is uniformly distributed. If we could stop time and look at just one instant of the foam, we would be confused, even terrified. Nothing would resemble anything else. Distances would deform without warning. Directions would disappear. The very notion of place would be impossible to define. And yet, that microscopic chaos is what allows the universe to function on large scales, for planets to orbit, for orbits to be stable, for time to make sense. Quantum foam is like the hidden heartbeat of the cosmos. We do not hear it because its rhythm is too fast, too deep, but everything vibrates in time with that beat. When we think of black holes evaporating through Hawking radiation, we must imagine that radiation as a direct product of the quantum foam being disturbed by extreme gravity. It is not that the black hole emits something voluntarily. What happens is that its boundary becomes an amplifier of fluctuations. The energy that emerges does not come from the interior. It comes from the vacuum, altered by the presence of the horizon. It is space itself that becomes the source of radiation. And here a revealing connection arises. If fluctuations can generate observable radiation, then they are leaving clues. We cannot see the foam directly, but we can infer its effects. Hawking radiation is one imprint. The fluctuations we see in the cosmic microwave background are another. Variations in the cosmological constant might be yet another. And yet, we are still far from understanding what the foam truly is. We do not know how it is organized. We do not know what laws govern its fluctuations. We do not know if the loops, filaments, or mini black holes that we imagine really exist. All we have are approximations, conjectures, and incomplete mathematical models. But what we do know is that black holes, in their extreme silence, force us to look toward that frontier. They are like spotlights illuminating the deepest level of space. Every paradox, every inexplicable phenomenon, every limit where relativity breaks down, points us to the fact that the true answer lies there, where space ceases to behave like a continuous fabric. Quantum foam is the territory where the next scientific revolution will be born. It will be there that quantum gravity finds its final form. It will be there that information, time, and space cease to be independent concepts and merge into something more fundamental. And perhaps, when we understand that level, we will discover that all the reality we know, galaxies, stars, black holes, even ourselves, is an emergent consequence of that microscopic dance. Like waves that appear solid but are nothing more than the surface expression of a much deeper ocean. There are moments in the history of science when the universe seems to stop to show us a glimpse of something we should not yet understand. A conceptual flash that appears as an intuition, a murmur at the limit of the thinkable. This happened when physicists began to suspect that reality might not be what it seems, that the three-dimensional world we inhabit could be, in a sense, a projection. Not an illusion, but a representation of something more fundamental. A surface that encodes every detail of the volume we think we occupy. This intuition arose, curiously, not by looking toward galaxies, nor toward the beginning of the cosmos, but by studying black holes, objects so extreme that trying to describe them forces us to rethink the very foundations of existence. It is no exaggeration. Black holes put our traditional understanding of reality into crisis and opened a possible path toward a holographic universe. The idea is not poetic by accident. It is deeply mathematical. And it arises when we try to answer a question that seems innocent. How much information can a black hole contain? In physics, information is not a metaphor. It is a real, almost tangible measure. It represents the details that describe a system, the position of each particle, its energy, its quantum state, its possible interactions. It is the set of instructions that make something what it is. Even a simple glass of water contains more information than we could record on all the computers on Earth. And when an object falls into a black hole, that information, in theory, should be stored somewhere. Not because we want it to, but because quantum mechanics requires that nothing be completely destroyed. The problem, as we saw before, is that the interior of a black hole does not seem to have enough space to store so much information, or at least not according to the classical view. But when Jacob Bekenstein began to analyze the issue, he discovered something surprising, almost disturbing. The amount of information a black hole can contain does not depend on the black hole's volume, but on its area. That is, not on what it occupies, but on its external surface, the event horizon. The larger the horizon, the more information the black hole can contain. But if we double its volume, the information does not double. It only increases according to the exterior area. Image illustrating the relation between black hole area and information entropy. It is as if, somehow, all the complexity of the interior were encoded on its skin. A skin that is not a physical object, but a limit, a geometric boundary. This idea was so strange that many scientists initially did not know what to do with it. But it was correct. Again and again, the calculations agreed. A black hole's information grows with its surface. Hawking confirmed that the entropy, a measure of disorder or information, of the black hole also followed this rule. And there, without anyone explicitly searching for it, a principle was born that would forever change our understanding of the universe: the holographic principle. Leonard Susskind, one of the most passionate defenders of this idea, explained it in a way that seems straight out of a science fiction novel. The universe could function like a hologram. In a hologram, all three-dimensional information is encoded on a two-dimensional surface. And it is not magic. It is physics. A hologram works because every point on the surface stores data that reconstructs the depth, texture, and shape of what we see. If we apply this analogy to the universe, it means something extraordinary. The three-dimensional reality we experience could be a manifestation of the information stored on a more fundamental boundary. Green expresses it elegantly. It is not that we live in an illusion, but that our three dimensions could be the internal interpretation of a deeper architecture. Instead of thinking of space as an independent volume, we could imagine it as an emergent phenomenon. And the initial clue toward that interpretation comes precisely from black holes. If a black hole can store all the information of its volume on its surface, why couldn't the entire universe do the same? It is a radical question, but also an inevitable one. If nature behaves in one way at an extreme, in black holes, where gravity is maximal, perhaps that behavior is not an exception, but the rule. Perhaps black holes are not anomalies, but windows. When physicists began to explore this idea, they found something surprising. The equations that describe certain quantum theories without gravity in 2 dimensions can be exactly equivalent to the equations of a universe with gravity in 3 dimensions. It is as if a flat world could contain all the information to generate a deep world. This correspondence was initially discovered by Juan Maldacena in the context of string theory, in what is now known as the ADS/CFT correspondence. Although the real universe is not exactly that type, the idea suggests a more general principle. Gravity could be an emergent manifestation of something more fundamental encoded on a boundary. But even without going into the details of Maldacena, Bekenstein, or Susskind, there is already a strong fact. Black holes behave like holograms, and if they do, perhaps space does too. When one thinks about this, the mind tends to imagine a flat universe, projecting inward like an inverted cinema. But it is not that. The hologram we are talking about does not require physical projection. It is a mathematical equivalence. What happens in a volume can be completely described by data on a surface. It is not a shadow. It is an abstract mirror. And that mirror is not located in a specific place. It could be the horizon of the observable universe, or a conceptual region not yet discovered. The idea is unsettling because it inverts our intuition. Throughout human history, we have assumed that reality is contained in objects, in volumes, in masses. But the holographic principle tells us that the essential might be on the boundaries, that the universe preserves its memory not in the deep, but on the surface. This also reinterprets the information problem. If the black hole horizon stores the data, then the information is never lost, even if the interior collapses. The hologram is on the surface, preserved in minuscule patterns that we cannot read, but which are there. Every particle that falls does not disappear. It becomes part of an encrypted mosaic. The surface is not just a limit, it is a book written in a language we do not know, and that the universe seems determined to hide from us. Every small ripple on the horizon could be a quantum bit, a fragment of the history of the fallen object. And although these patterns cannot be observed directly, their existence is necessary for the universe to maintain its coherence. Thorne points out that this approach changes our view of black holes. They are no longer sinks, but archives. And if we take this idea to the extreme, we could conclude something even deeper, that reality itself is an archive, that what we see as space is an internal processing of data stored on a distant boundary. Imagining the universe as a hologram has a beauty that does not depend on metaphors. It arises from mathematics, but resonates in philosophy. It forces us to ask ourselves what it means to be inside something. What does occupation, volume, and distance mean? If the information is on the surface, then the interior might be an interpretation, a consequence, not an origin. The hologram does not deny our dimensions, it reinterprets them. It is not suggesting that we are flat. It is saying that our three-dimensionality could derive from something else, from a deeper principle, just as temperature is not a fundamental property, but the statistical result of the movement of thousands of molecules. Thus, space might not be fundamental, but emergent. Green explains that this is not a degradation of reality, but a discovery. That something is emergent does not make it less real. Music emerges from vibrations, color from frequencies, life from chemistry, consciousness from bioelectrical processes. The emergent is not false, it is complex. Imagine someone telling you that the volume of the universe is a consequence of information distributed on a conceptual boundary. Not that it is a cinematic projection, but that the equations describing what you see have a perfect equivalent on that boundary. It is like discovering that an unknown language can narrate exactly the same stories as your native tongue. Two different descriptions, one single reality. The holographic principle suggests this. Two distinct frameworks tell the same physical story. If this is true, or even partially true, then black holes are the key pieces of the puzzle. Not because they destroy things, but because they reveal them. They were the first objects in which the surface proved to be more important than the volume. Their quantum behavior forces the size of the horizon to be the actual measure of their information capacity. It is as if, at the most violent extremes of the universe, nature shows its deepest rules. The idea of a holographic universe also opens doors to unsettling questions. If the three-dimensional is emergent, then what force causes it to arise? What mechanism translates the data on the surface into the internal experience of volume? Green admits that we still do not know the answer. It is an open mystery. We know the mathematical equivalence exists, but we do not know how it is physically realized. It is like having a dictionary between two languages, but without knowing the country where that original language is spoken. But perhaps the most provocative implication is the philosophical one. If the universe's surface stores all the information, then what we see is not the universe itself, but an internal interpretation of that information. Not an illusion, but an interface. An interface like a computer screen. It does not show you the electrical circuits. It shows you a processed image that makes sense to you. And it is not as strange as it seems. The brain does something similar with everyday reality. We do not perceive atoms or electromagnetic waves directly. We perceive interpretations, colors, sounds, textures. Physical reality does not have colors or sounds. They are constructions of our nervous system. What we believe is real is an interface designed for survival, not direct access to the truth. If the brain works this way, why couldn't the universe itself work this way? A hologram does not deny the existence of space. It explains it in another way. When a black hole grows, its surface increases. When it merges, the resulting surface preserves the holographic principle. Even when it evaporates, if the horizon hologram is capable of transforming the information into Hawking radiation, then the process is complete. Nothing is lost. Everything is transcribed. This suggests that even if the black hole's interior completely collapsed, the holographic description would still be valid. The volume might disappear, but the surface, as long as it exists, holds the history. And when it ceases to exist, the information it contained has already been distributed somehow to the outside. Some physicists imagine that the horizon is composed of atoms of space, discrete units that contain bits of information. We do not have a complete theory of those atoms, but we know that their minimum area would be determined by the Planck scale. That is, the surface is pixelated. Each pixel contains something, and the total number of pixels determines how much information it can store. It is an absolutely distinct view from the smooth surface we usually imagine. A surface so dense with information that it contains the complete history of everything that fell into the hole. The three-dimensionality of the interior would be a consequence, not a requirement. Over time, these ideas have expanded. Now we not only talk about black holes, but about entire regions of space that could have holographic descriptions. The early universe, extremely hot and dense, might have had a dual geometry equivalent in one dimension less. The fluctuations we observe in the cosmic background could be the three-dimensional shadow of two-dimensional processes. Still, we must not be tempted to think that this makes the universe less real. It is not a simulation. It is not a fantasy. It is a physical structure with precise laws, with energies, with dynamics. It is simply that what we see from within could be the three-dimensional expression of something encoded on a boundary. The question then changes. It is no longer what is the universe, but from where are we viewing it? Green insists that these interpretations do not contradict everyday experience. They do not nullify our three-dimensionality. They only explain it from a broader perspective. And in the end, that is the true strength of the holographic principle. It does not destroy our understanding, but recontextualizes it. Black holes, far from being anomalies, become teachers. They show us that space can be stranger than we imagined, but also more ordered, that boundaries matter, that the surface is as fundamental as the interior. Since childhood, we are taught that the world has three dimensions. We can move forward or backward, left or right, up or down. Three directions seem sufficient to describe absolutely everything that can happen in our environment. And for centuries, that intuition worked. We built cities, airplanes, bridges, telescopes, and entire theories thinking only in those three dimensions. But as we explored the very small and the very large, the universe began to behave as if it were hiding a secret that had been there from the beginning, hidden right in front of our eyes. Something like finding a door where we always thought we saw a wall. That secret is the possibility that extra dimensions exist. Not 3, but perhaps 10, 11, or even more. Not imaginary dimensions, not magical worlds, but real parts of the fabric of the universe that are so well folded, so compacted, so outside our everyday scale, that we simply cannot perceive them. Brian Greene explains it with a simple image. If you look at an electrical cable from afar, you see it as a thin line, like a single thread. But if you get very close, you discover that it is not a line. It is a cylinder. It has thickness, internal space, perhaps even several wires inside. The distance between you and the cable determines what you see. And the exact same thing happens with dimensions. From our human perspective, the universe seems to have only 3 directions. But if we could get close enough, if we could observe space on microscopic scales millions of times smaller than an atom, we would see that what today looks like a straight line could actually hide an entire invisible geometry, delicate as embroidery and complex as a labyrinth. The inevitable question is, why would the universe need more dimensions? Why include something that no one can see? The answer is born in fundamental physics. As scientists tried to unite all the forces of nature, gravity, electromagnetism, the strong and weak nuclear interactions, they found themselves with equations that only worked if the universe had more dimensions than we can perceive. It is not that they wanted them. The mathematics simply demanded that additional space. As if nature refused to function in a purely 3-dimensional world. String theory was the first to suggest it strongly, for the fundamental strings of the universe to vibrate correctly, for particles and forces to emerge from those vibrations, Space had to have additional dimensions. It was not a whim, it was a mathematical necessity. Gravity, which had always been the most rebellious and difficult force to integrate, only behaved correctly when the equations expanded beyond what our senses can grasp. Green explains it with a metaphor. Imagine trying to play a complex melody on an instrument that only has 2 notes. It is impossible. You need more keys, more musical space. The same thing happens with the universe. For all the physical laws to be in harmony, the cosmos needs more geometric keys. But if hidden dimensions exist, why don't we see them? Why can't we walk toward them, explore them, or photograph them? Because they are curled up on themselves on tiny scales. They are not extended like the 3 visible dimensions. They are compacted into structures so small that not even light can reveal their shape. It is like having an entire world hidden inside a speck of dust, coiled into a size so small that it would be like trying to see the inside of a hair with the naked eye. Green compares these dimensions to small circles or spheres attached to every point in space, but so microscopic that on our scale they seem not to exist. They are sometimes described as pocket dimensions because they are there, but no one can enter them. They are too narrow, too folded. However, even if we cannot access them directly, they affect everything that happens in the large dimensions. They are like invisible foundations that support a building. You do not see them, but without them, the building would not exist. One of the most beautiful revelations of this idea is that the properties of particles could depend on the shape of these hidden dimensions. The mass of a particle, its charge, and even its quantum behavior could arise from how those dimensions fold and vibrate. It is a profoundly aesthetic image. The characteristics of the visible world could be the amplified echo of a minuscule geometry, hidden in the heart of space. Green uses the analogy of a flute. The shape of the instrument determines the sounds it produces. Similarly, the shape of the hidden dimensions determines the particles that exist in our universe. If the dimensions were different, the music of the cosmos would be distinct. New particles, new laws, even a totally unknown universe could appear. It is a dizzying thought. Perhaps what we call reality is nothing more than a particular melody played over a hidden geometry. This idea also opens the door to something even more fascinating: parallel universes. Not in the simple sense of duplicated worlds, but as natural variations of space-time according to different configurations of the hidden dimensions. Each possible shape of these dimensions could generate a universe with different laws. In one, gravity might be stronger. In another, stars might live only a few minutes. In another, the concept of an atom might not exist. Each hidden geometry would be like a different musical score that the universe interprets. And although we will explore this part later, it is enough here to understand that hidden dimensions are not a mathematical luxury. They are a powerful mechanism that could explain why the universe is the way it is, why the particles that exist, why the forces have their current intensity, and why we ourselves are possible. However, there is something deeper in this story. When we imagine extra dimensions, we tend to think of them as alternative routes within space, like secret doors or invisible paths. But it is not like that. We cannot walk toward them because they are not oriented in the same direction as the other dimensions. They are folded in a different way, at angles that do not belong to our way of moving. It is as if you tried to walk toward the color red. There is no spatial direction toward red. Color is a property that emerges from another dimension, that of the electromagnetic spectrum. Trying to reach it with your legs makes no sense. The same happens with hidden dimensions. They are not accessible through physical movement, but through properties of deep physics. In fact, some particles can feel these dimensions. The particles related to gravity, the hypothetical gravitons, could travel through them, and this has enormous consequences. It could explain why gravity seems so weak compared to other forces. Perhaps it is not weak at all. Perhaps it is simply dispersed in dimensions that we cannot see. Like trying to listen to someone speaking from another room. It is not that they are whispering, but that their voice is dispersed in a space that you cannot perceive. If this is true, black holes would also be sensitive to these dimensions. In fact, some models predict that they could adopt different shapes depending on how those hidden dimensions are configured. They would not be perfect spheres, but more complex objects where gravity is distributed differently. They could even produce specific quantum phenomena that we have not yet detected. The relationship between black holes and hidden dimensions is profound. Black holes curve space so extremely that if folded dimensions exist at every point, that curvature could stretch them, flatten them, or even make them vibrate. They are like giant hands squeezing a delicate fabric. Every gesture reveals something of the microscopic weave that is normally hidden. But there is something even more unsettling. If extra dimensions exist, then the singularity inside a black hole might not be a point. It could be extended across those hidden dimensions. It could be a more complex structure, a region where the three-dimensional geometry collapses, but the hidden geometry continues to exist. A kind of mathematical refuge where physics still has rules. And this means something gigantic. The interior of a black hole could be much larger than we think, not in our dimensions, but in the others. A place where space collapses in three visible directions, but expands in several invisible ones. We cannot imagine it, just as a fish living in two dimensions could not imagine the concept of up. But mathematics can. And when mathematics speaks insistently, sooner or later, nature usually proves it right. Green recalls that when Einstein proposed that gravity was a curvature of space-time, the idea seemed impossible to visualize. No one knew what it meant to curve time. No one knew how a clock could tilt, just like a line. But little by little, the evidence accumulated until that revolutionary idea became part of our everyday understanding. Something similar could happen here. Hidden dimensions seem extravagant today, but perhaps in the future they will be as obvious as the idea that the Earth revolves around the sun. And in that future, the structure of those dimensions could be the key to understanding quantum gravity, information in black holes, the origin of the universe, and even the final destiny of the cosmos. Hidden dimensions do not just expand space, they expand what it means to exist, and therein lies their true power. They force us to admit that reality is deeper than our intuition, that the universe is not limited by what we can touch or see, that the visible is barely a part of the whole, just as the bark is merely the container of an immense tree. There are ideas that do not fit into a single reality. Ideas that, when they first appear, seem too big for our world, too free for the way we usually understand existence. The concept of parallel universes is one of them. When someone hears it for the first time, they usually think of alternative versions of themselves, duplicated lives, events that happen differently. But what modern physics proposes is much deeper, stranger, and, in a way, more humble. The possibility that our universe is not unique, but one among an immense variety of realities, each with its own laws, its own space, its own time. Image illustrating the multiverse concept, multiple bubbles or regions of distinct realities. Brian Greene explains that this idea does not arise from simple imagination. It arises because mathematics, cosmology, and quantum physics begin to point in that direction, almost without anyone looking for it. It is like following a map without knowing you are following a map. When physicists try to solve some of the most difficult questions in the universe, how everything began, why the physical constants have their values, how particles behave, they ended up colliding with a disconcerting possibility that our reality might be just one version among many. But before imagining portals or personal duplicates, it is worth understanding that each type of multiverse is distinct. They are not copies of the universe, but different forms of existence that emerge from different disciplines of physics. Some versions are more intuitive, others are so profound that we can barely visualize them. Still, they all share something: the feeling that the cosmos could be much wider than any telescope can capture. Let's imagine the simplest multiverse first, the cosmological multiverse. When scientists studied the Big Bang and the expansion of the universe, they realized that there was nothing in the equations that forced the universe to have a limited size. It could be infinite, totally infinite. And if it is infinite, then all possible configurations of matter should repeat somewhere. Not because there are magical duplicates, but because when you have an infinite board with finite pieces, patterns inevitably begin to repeat. If this is true, in some unimaginably distant region, there could exist a galaxy identical to ours, a planet identical to Earth, even a person identical to you reading these very words. Not because there are copies, but because the mathematics of infinity demands it. It is a disconcerting perspective. It does not imply that those versions are connected. They cannot influence us, nor can we influence them. They are so far away that light, even traveling since the beginning of time, could never reach them. They are like islands separated by oceans that can never be crossed, universes within the same universe, inaccessible regions, bubbles of reality that will never touch. But that is only the first level. The second multiverse arises from cosmic inflation, a theory that describes how the universe expanded at an overwhelming speed just after the Big Bang. The surprising thing is that this inflation does not have to be happening only here. It could be happening in different regions of space, independently, creating bubbles of the universe that inflate, separate, isolate themselves, and grow as universes of their own. Our observable universe would be one of those bubbles. And other bubbles, with different physical laws, could exist beyond what we can ever see. In this scenario, each bubble is a universe, and the collection of all bubbles is a multiverse. Some universes might have more dimensions, others might have different physical constants, and others might never form stars. Imagine a tree whose trunk is eternal inflation and whose branches are independent universes, each evolving according to its own rules. We inhabit only one branch, but the others continue to grow in silence, invisible, unreachable. Then there is the quantum multiverse, perhaps the most disturbing from a philosophical point of view. It arises from the many worlds interpretation of quantum mechanics proposed by Hugh Everett. This interpretation suggests that every time a quantum event with multiple possibilities occurs, they all occur, but in different universes. In one of those universes, an atom decayed. In another, it did not. In one, a star exploded. In another, it did not. If we take this idea to the extreme, then every decision, every possible outcome, every variation of history branches off into a new universe. At first glance, this may sound exaggerated, but Green reminds us it is not fiction. It is about following the mathematics of quantum mechanics without imposing arbitrary collapses. The equations do not say that only one possibility occurs. They say that all possibilities exist in superposition. The quantum multiverse simply takes that superposition seriously and translates it into parallel universes that evolve independently. In one of those universes, perhaps you took a different job. In another, you never met certain people. In another, you made a decision that completely changed the trajectory of your life. But none of those universes are accessible from ours. There are no bridges. There is no communication. They are like shadows of possibilities that existed at some point, but that now continue their course without us. Then there is the string multiverse, which is even more abstract. According to string theory, the hidden dimensions we discussed earlier can take different shapes. Green explains that these shapes, called Calabi-Yau manifolds, can exist in a virtually infinite number of configurations, and each configuration determines the physical laws of the universe that emerges from it. Thus, each shape of these dimensions could be the basis for a completely different universe. Not branched universes, but universes with fundamentally different structures. In one of them, electrons might have a different mass. In another, gravity might behave strangely. In another, matter might not exist as we know it. This multiverse does not result from decisions, nor from inflation, nor from spatial infinity. It arises from the geometry and fundamental vibrations of space. It is a multiverse of mathematical possibilities. As if the universe were capable of playing millions of different melodies, but we only hear one. But Green goes even further. He suggests that a simulation multiverse could exist, not in the human technological sense, but as a consequence of the laws of physics. If the universe can generate structures capable of simulating other realities, and those realities can simulate others, the chain of universes might be endless. But this terrain is more speculative, and we do not need to delve too deeply into it to understand that the essential idea remains the same. Reality could be much vaster than we can encompass. The interesting thing is that, although these versions of the multiverse seem distinct from each other, they share a common thread. They are born out of necessity, not fantasy. Inflation naturally leads to universe bubbles. Quantum mechanics, when taken literally, naturally leads to multiple simultaneous histories. String theory, by trying to unify all forces, naturally leads to hidden dimensions with multiple configurations. And infinite space naturally leads to inevitable repetitions of patterns. We are not inventing worlds just for the sake of it. We are following the clues the universe leaves behind. The emotional part comes when we think about what this implies. For centuries, we believed that the universe was unique, singular, complete by itself. But if a multiverse exists, then our existence is merely one variation among many. It does not diminish our value. It simply places us in a broader perspective. Like discovering that an enormous ocean contains millions of waves and that we are one of them. Perfectly real, perfectly valid, but not unique. Paradoxically, this idea can be liberating. The multiverse does not erase us. It multiplies us. It shows us that the creativity of the cosmos is so great that it is not satisfied with a single reality. It prefers all of them. It is not limited to one combination of laws, but explores all that are mathematically possible. It does not settle for one result. It unfolds a range of possibilities. Some universes might be teeming with life. Others might be absolutely silent, without atoms, without light. Some might last a cosmic blink. Others might expand eternally. And we are here, in a particular version, wondering why this universe has the laws it has. The answer might be as simple as it is profound, because in other universes, the laws are different. In our universe, stars shine for billions of years. In others, they might burn out before they are born. In some, gravity would be too strong to allow planets. In others, too weak to allow galaxies. And we exist precisely in a universe where the conditions are suitable for complexity to flourish. Not because this universe is special, but because universes where complexity cannot exist never have observers wondering why they exist. It is a mix of humility and wonder. We are not central. We are not the center of the cosmos, but we belong to its deepest architecture. We are one story among thousands, and yet a story that can only happen here, with these laws, with this physics, with these conditions. Green insists that the multiverse is not an intellectual escape, but a consequence of taking the best theories we have seriously. And although we still cannot directly observe other universes, we can infer their existence through calculations, analogies, symmetries, and equations. Physics, like art, can see the invisible. The most beautiful thing is that, upon reaching this point, it is no longer about counting universes as if they were objects. It is about accepting that reality can be larger than what fits into a single description. The multiverse does not ask us to renounce our experience. It asks us to expand our conceptual framework. It invites us to imagine a cosmos where every possibility exists somewhere, where every configuration of reality finds its home in a branch, in a bubble, in a vibration. And yet, even if thousands of universes exist, ours is still unique to us. It is full of our stories, our memories, our fears, our dreams. We are conscious in this version, in this particular corner of the whole. That already makes it special, not for being the only one, but for being ours. For decades, black holes have been described as the most extreme places in the universe, regions where gravity becomes so intense that not even light can escape, regions where time stretches, where matter loses its identity, where space curves until it touches its logical limit. However, as science advances, black holes are beginning to reveal an even more unsettling dimension. They might not only be astrophysical objects, but points of contact with other realities, places where the laws of our universe become so strained that they might allow others to exist. This is an idea that appears in different ways in modern physics. Sometimes it arises in quantum theory, sometimes in relativity, sometimes in string theory, but in all of them, there is a pattern. Black holes are frontiers, frontiers between the space we know and the space we perhaps cannot see, frontiers between the history we live and the histories that physics does not rule out. To begin to understand this connection, it is helpful to imagine a black hole not as a dark void, but as a region where space curves to absolute extremes. There, what we understand as directions ceases to behave in a known manner. The trajectories of particles are no longer smooth lines, but deformed routes, almost like paths that twist back on themselves, trying to follow some logic that we do not yet comprehend. In that terrain, geometry has a behavior that is unlike anything else in the visible universe. The first thing that connects black holes with the idea of parallel realities is the concept of extended spacetime. According to general relativity, if we could see the entire geometry of a black hole all at once, not just the exterior part, but also what happens behind the horizon, we would discover that its mathematical structure allows for internal regions that, in principle, do not belong to the same space-time we inhabit. It is not that they are other universes, in a traditional sense, but rather regions disconnected from our exterior. Separate regions, where the timelines can no longer rejoin ours. This simple idea suggests something profound. A black hole creates an interior that is not causally connected to our world. We cannot send a message in there. We cannot receive news from inside. We cannot see what happens. It is as if, upon crossing the horizon, the universe reacted by closing the door from the inside. And that, in itself, is a form of separation between realities. Not because they are different universes, but because they are regions of space-time that no longer share continuity with us. But this is only the beginning. Another bolder connection arises when analyzing what happens at the singularity. The singularity is the region where the curvature of space-time becomes infinite and where general relativity ceases to be reliable. Green explains it with a beautiful metaphor. The singularity is not a physical point. It is a mathematical announcement that screams that the current rules no longer work. It is the equivalent of trying to divide by zero. Something breaks, and when the rules break, new behaviors can emerge. Some physicists have suggested that the singularity could be a neck connecting our universe with another. Not a stable tunnel or an open door, but a region where space-time could reorganize into a separate structure. If this were true, then every black hole could be generating a new universe in its interior, a baby universe that expands inward while we, from the outside, only see an object that seems to devour matter. There is no experimental evidence to confirm this, but there is a mathematical basis that does not rule it out. And that, in theoretical physics, is enough to take the idea seriously. Another important link arises when analyzing the quantum behavior of black holes. Quantum mechanics suggests that information cannot disappear, but black holes seem to swallow everything without a trace. This contradiction, the famous information paradox, led physicists to seek solutions that would not destroy information. One of the most striking proposals is that information does not disappear, but could escape into another region of space-time, perhaps even into another reality. In this view, black holes would act as intermediaries that allow information to travel to places that our universe cannot contain. This opens the door to a more radical interpretation. Black holes could be natural connections between different regions of the multiverse, not navigable or controllable connections, but points where the structure of space-time becomes extreme enough to blend the boundaries between realities. Another fascinating line appears with wormholes. Although we have not observed any, their equations emerge as valid solutions of general relativity. A wormhole is a kind of tunnel that connects two regions of space-time. They could connect 2 points within the same universe or 2 different universes. The idea is not that a black hole is a wormhole, but that its mathematical structure resembles, in some aspects, the structure needed for a bridge between realities. If space-time is capable of deforming to that extent, then the possibility of connected universes ceases to be a fantasy. However, Green clarifies something important. Even if these mathematical bridges exist, nothing indicates that they are stable. Such a tunnel would collapse almost instantaneously. But the key is another. Physics does not rule out the existence of universes connected through extreme regions. It only rules out that we can travel through them. Another connection between black holes and parallel realities appears when we think about quantum evaporation. A black hole is not eternal. Hawking showed that it emits radiation and eventually disappears. The traditional image says that the black hole shrinks until it completely disappears. But the quantum image is more complex. When the black hole reaches the end of its life, all the geometry around it changes. And in that final change, a phenomenon so abrupt could occur that it triggers the formation of a new region of space-time. In other words, the black hole could die by creating a separate reality. Just as a star collapses to form a black hole could collapse to form a distinct universe. There are even bolder theories. Some suggest that the physical constant of a universe could mutate when a black hole creates a baby universe. It is as if each universe could have offspring, and each offspring had its own laws. This idea is called cosmological selection, and it proposes that universes that generate more black holes are more fertile and therefore more common in a self-reproducing cosmic landscape. In this scenario, we would exist in a universe that, by chance, is optimized to generate black holes. Not because there is an intention, but because, in a reproductive multiverse, the universes that generate more offspring become more frequent. But there is an even more surprising interpretation. Some variants of quantum theory suggest that every time a black hole captures information, that information could live in a kind of parallel reality. It would not be a completely separate universe, but an extension of our own universe on a level that we cannot perceive. This connects with the holographic principle, which says that the information contained in a volume of space can be encoded on its boundary. If this is true, then the black hole's boundary, its horizon, could be a surface where the information of a reality that exists behind that boundary is projected. It is as if every black hole were a screen, an interface, where our universe touches something it cannot describe with its own laws. We do not have access to what is happening on the other side, but we can see its shadow. There is an additional detail that appears in string theory. According to this framework, space is not a uniform fabric, but a vibrating structure that can be divided into layers. Some vibrations correspond to particles in our universe, but others could correspond to particles that exist in parallel universes. And most importantly, regions of extreme curvature, like black holes, could allow these vibrations to interact with each other. It does not mean we can travel to another universe, but that on the deepest scale, a black hole could be a place where the boundary between two universes is less rigid. Another possibility that arises is that black holes are the only places where the landscape of possible universes can change. String theory suggests that there are thousands of possible configurations for the hidden dimensions. Each configuration generates a universe with distinct laws. If a black hole alters the curvature of these dimensions, it could trigger a change that separates a region of spacetime into an independent universe. Suddenly, a black hole stops being a final destination to become a starting point. Beyond all these theories, there is a deep emotional aspect to this connection between black holes and parallel universes. Black holes represent limits, what we cannot see, what we cannot cross, what we cannot measure. And parallel universes represent possibilities. What could exist? What could be different? What could be happening outside our perception? The idea that both could be related is almost poetic. It is as if every limit of the universe were also an invitation to imagine other forms of reality. The connection between black holes and multiverses is not definitive. There is no theory that unifies everything conclusively, but modern physics does not rule it out, and that, in this field, is equivalent to saying that the idea is alive, that it is worth exploring, that it could reveal something we do not yet know how to ask. Perhaps we can never see what happens behind the horizon. Perhaps we will never know if a black hole leads to another reality or if it is simply a silence of space. But the important thing is what it reveals, that the universe is larger than our certainties, deeper than our intuitions, bolder than our questions. If black holes are doors, we do not need to cross them to feel wonder. It is enough to know that they exist.